Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 2.6 from your textbook, which was our introduction into the concept of inverting a matrix. In the previous video, we established a lot of results about the inverse of a square matrix. Namely, we figured out that the inverse of a square matrix exists if and only if the rank of that matrix is full, meaning that the rank of the matrix is equal to the number of rows and columns. We also found that a process for finding the inverse of a square matrix, if it exists, can be done by augmenting the matrix with the identity matrix, using elementary row operations to modify the matrix, if possible, into the identity matrix, and then the result of those applied to the identity matrix will be our inverse. In this video, we're going to take a look at one quick example of, again, sort of doing that process and seeing if the inverse exists, and if so, what is that inverse? And then we'll look at some properties of the inverse of a matrix. So in this, we won't be establishing sort of any results about when an inverse exists, but more be focused on sort of the properties of the inverse of a matrix. But to start off with, let's go ahead and take a look at just another sort of computational example of determining the inverse of a matrix if it exists. So we've got this 4x4 square matrix. Remember, again, for our class, the inverse of a matrix is only a concept that we're applying to square matrices, so it has to be square here to even begin. To start off with, we'll go ahead and we'll augment this with the identity matrix. So we'll have this matrix here, and then we're going to augment that with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And then our goal is to take this left matrix here and use elementary row operations to eventually convert that into the identity matrix. If we then track what happens to that along the way, well, if we apply those elementary row operations to this, what results over here will be a inverse. Now, of course, if along the way we find out that this has a rank less than 4, then we know that the inverse will not exist. So in this case, we have this 1 here in the pivot position, so we can just use that immediately to start clearing out things in that first column. So let's begin by doing row 3 and replace row 3 with row 3 minus row 1, and we'll replace row 4 with row 4 minus 2 row 1. So the first two rows won't change. We'll have 1, 2, 3, 0, 0, 1, 0, 1. Then we're subtracting row 1, so it looks like we're going to get 0, and then negative 1, and then negative 2, and then 1 minus 0, so it's 1. Then we're doing R4 minus 2 row 2, so it looks like we're going to get 0 there, and then 4 minus 4, so 0, and then 4 minus 6, which is going to be negative 2, and then 2 minus 0, which is going to be 0. 2 minus 0, which is going to be 2. There we go. Okay, so we've got that, and then we also need to do that on the other side. So we have 1, 0, 0, 0, 0, 1, 0, 0. Then we did R3 minus R1, so it looks like we're going to get minus 1, 0, 1, 0. And then we did R4 minus 2R1, so we're going to get minus 2, 0, 0, 1 there. Okay. So now this looks good. Notice we have a 1 in this pivot position, so we can start to use this and apply this to remove this down here to, again, get this into row echelon form. So we can go ahead and do R3 and replace R3 with R3 plus R2. When we do that, we get 1, 2, 3, 0, and 0, 1, 0, 1. Then we're adding row 3 to row 2 to row 3. So we'll get 0, 0, negative 2, and 2. And then we're not modifying row 4, so we still have 0, negative 2, 2. Then here we have 1, 0, 0, 0, 1, 0, 0. We added row 2 to row 3, so now we have negative 1, 1, 1, 0. And then we have negative 2, 0, 0, 1. Okay, at this point, we could go ahead and divide by negative 2 here to get a leading 1, but we can be a little bit more clever and notice that this matches this exactly. So if we just simply subtract row 3 from row 4, we're going to get a 0 row there, and that's going to be good enough for us to realize that this thing is not going to be invertible. So let's go ahead and do that. Let's take row 4 and replace row 4 with row 4 minus row 3. So we have 1, 2, 3, 0. 0, 1, 0, 1, 0, 0, negative 2, 2, and 0, 0, 0, 0. And then, of course, over here we have 1, 0, 0, 0, 0, 1, 0, 0, negative 1, 1, 1, 0, and then we subtracted that. So it looks like we'd get negative 1, negative 1, negative 1, 1. But it really doesn't matter over here because we can notice right here that this thing is going to have a 0 row, so this is not going to have full rank. Actually, if we took it one step further and we did divide by that negative 2, we could actually see that we will have 3 pivot positions. You can even notice that from here. I wouldn't say that this is in row echelon form because it doesn't have a leading 1, but you could sort of call it quasi-row echelon form. It does have leading values in each thing. Main point, though, is we can tell that the rank of our matrix here is equal to 3, which is less than 4, which implies not invertible here. So since we got that sort of 0 row right there, that meant it wasn't going to have full rank, and it's not invertible. We actually were able to determine the rank too, because we could actually see that it was going to be 3. So along the way, we also determined the actual rank. Okay, so this was again another sort of just computational example of starting with a matrix and attempting to find its inverse. Here, the example we did at the very end of the previous video, we were able to find the inverse by doing this process. In this case, because we got that 0 row, that told us that the rank was less than full, which means it's non-invertible. Okay, now we should be comfortable with the process of determining an inverse. Let's turn our attention to some properties of inverses. So these are properties of the inverse of a matrix. So in all 3 of these properties, we're assuming that the matrices A and B have inverses. So we're going to let A and B be invertible matrices. These are then properties that apply to invertible matrices. So the first one is pretty clear. It says that A inverse, so the inverse of a matrix, is also invertible. And the inverse of an inverse, as you would expect, is equal to the original matrix. So the inverse of the inverse is the original matrix. Property 2 says that if A and B are both invertible, then their product is invertible. So if you multiply 2 invertible matrices, you're guaranteed to get an invertible matrix. And the inverse of the product is the inverse of the second matrix times the inverse of the first. So you'll notice that we're basically saying that the product, the inverse of the product, is the product of the inverses, but in reverse direction. So very important to recognize here that it reverses the direction here, or the order of the multiplication, if you so choose. Also, last property here is that if A is invertible, A transpose is also invertible. So the transpose of an invertible matrix is also invertible. And the inverse of the transpose is the same as the transpose of the inverse. So in other words, transpose and inverse can be sort of flipped. If you want to do the transpose first and then the inverse, or the inverse first and then the transpose, it's the same result. All 3 of these results are proven in your textbook. I'm going to just go through a quick proof of property 2. You can read through or try properties 1 and 3 on your own. But let's do a proof of property 2. So we get to assume A, B invertible, which means A inverse, B inverse exist. We need to show AB invertible with AB inverse equal to B inverse A inverse. So what do we actually need to show? We need to show that AB times this AB inverse is going to be equal to the identity matrix, and we need to show that AB inverse times AB is equal to the identity matrix. So we need to show these 2 things. So let's go ahead and do that. Let's start with this one. So AB inverse. According to our assumption, AB inverse is supposed to be equal to B inverse A inverse. So let's see. AB B inverse A inverse. Then we can group these 2 together, and we should get A IN A inverse. Why is that? Well, because by assumption, B inverse exists, and B is invertible, so B times its inverse has to be the identity matrix. Then A times the identity matrix is simply just A, so this is AA inverse, and that equals the identity matrix. Check. Okay, then let's go ahead and try AB with what we're claiming is AB inverse. So we're going to do that the other way. So now we need to take AB inverse and multiply it with AB and see what we get. according to our claim, this AB inverse is supposed to be B inverse A inverse. So let's actually see if that works. Once again, group the stuff in the middle. A inverse A, by definition, is going to be the identity matrix. Then the identity matrix times that, well, clearly that's going to just be B inverse B. And then, of course, that is by definition the identity matrix. So that works. So what we just showed is that if we say that the inverse of AB is B inverse A inverse, then when we multiply AB with B inverse A inverse on either side, we get the identity matrix. So that means AB really is invertible because that is its inverse. Remember, if you can find an inverse, that shows something is invertible. Okay, so if you want to try property 1 or property 3 on your own, feel free to do so. You should be able to do sort of a similar proof to this by taking what the claimed inverse is, multiplying it once on the right-hand side and then the other on the left-hand side, and showing that both of those expressions ultimately reduce to the identity matrix. For now, though, instead of proving properties 1 and 3, because you have those in your textbook, we're going to extend the proof of property 2 to any amount of matrices being multiplied together, not just a pair of them. So we're going to extend property 2, and we're going to let A1, A2 through AN be invertible n by n matrices. I guess we shouldn't have the same subscript there. Doesn't really matter. This n and this n technically could be different. That's okay. Then what we're going to do is we're going to show that the product A1, A2 through AN is invertible, and the inverse of that product is the product of the inverses, but in the reverse order. So to do this proof, because we have an arbitrary amount of matrices, we're going to need to do a proof by induction. So the base case, the first multiplication, where it would actually be a multiplication, would be 2 matrices. So n equals 2. So what we would need to show is we would need to show that A1, A2 inverse is equal to A2 inverse, A1 inverse. Now, is there anything to do here? Well, no, because this is exactly property 2 that we just proved. We just proved this as property 2. So we're all done there. So our base case in this case is exactly property 2. So we can now move on to the inductive step. So our inductive step, we're going to assume that A1, A2 down to AK inverse is AK inverse, A2, or sorry, A2 inverse, A1 inverse. So we're going to assume that it holds for K amount of matrices. So if you multiply together K matrices, you can do this. And what we need to show is we need to show that if we had A1, A2 down to AK, and then another one, AK plus 1 inverse, that would be equivalent to AK plus 1 inverse, AK inverse, all the way down to A2 inverse, A1 inverse. So that would be our need to show. So let's go ahead and do that. We'll start with this left-hand side. So we have A1, A2 down to AK, and then AK plus 1 inverse. What we're going to do is we're going to do some clever grouping. We're going to view this giant group, the first K of them, as one matrix, and this one as a second. Now, by the base case, we know that if you have the product of 2 matrices and you're inverting it, you can do them individually and reverse the order. So this should be equal to AK plus 1 inverse times A1, A2 down to AK inverse. So what we did there is we switched the order of these two, treating this first K being multiplied together as a single matrix. Now notice that right here, this is your inductive hypothesis. So you get to assume that this is equal to AK plus 1 inverse. And then this right here, we assumed is equivalent to this. So this is AK inverse down to A2 inverse, A1 inverse. And that's by the inductive hypothesis. And notice that that is exactly what we wanted to show. So we're all done there. So this shows us that if all of the individual matrices are invertible, so again, they all have to be invertible. This doesn't work if some of them are not invertible. But if all of the individual matrices are invertible, then you can invert their product by simply taking the inverse of each of them and multiplying them in the reverse order here. So I wanted you guys to see this too because it's a nice little proof by induction and it's a good extension of the property that we originally established. So this extends property 2 to an arbitrary amount of matrices. Okay, so those were some basic properties of inverses that we wanted to discuss. The next thing we'd like to do is talk a little bit about a very special type of matrix that sort of relates this inverse with one of the very early matrix operations we discussed, the transpose. So we're going to give a definition here. A matrix A is said to be an orthogonal matrix if A inverse equals A transpose. So this is a very special subclass of matrices whose inverses are equivalent to their transposes. So let's determine if the following matrix is orthogonal. So we have this matrix here. A is the square root of 3 over 2, 1/2, negative 1/2, square root of 3 over 2. And we'd like to know if it's orthogonal. Well, notice we could come up with A transpose very easily. A transpose, if we do this, this first row would become the first column, so it would be root 3 over 2, 1/2. And the second row would become the second column, so minus 1/2, root 3 over 2. Now, how would we check if A transpose is A inverse? Well, we can just check by multiplying. So let's check A transpose equals, in this case, I2, and A transpose A equals I2. So let's start with this one. So that would be root 3 over 2, 1/2, negative 1/2, root 3 over 2, times root 3 over 2, negative 1/2, 1/2, root 3 over 2. So we're going to do this row times this column. Root 3 over 2 times root 3 over 2 is going to be 3 over 4. 1/2 times 1/2 is going to be 1/4. 3/4 plus 1/4 is going to be 1. Then this row times this column, that's going to give us negative root 3 over 4. And then this times this is going to give us root 3 over 4. Add those together and we get 0. This times this, that's going to be negative root 3 over 4. And then this times this is going to be root 3 over 4. Add those together and we get 0. And then this times this, well, negative 1/2 times negative 1/2 is positive 1/4. Root 3 over 2 times root 3 over 2 is 3 over 4. 1/4 and 3/4 adds up to 1. So that's halfway. Now we got to check the other direction. So now we need to take A transpose, which is root 3 over 2 minus 1/2, and 1/2 root 3 over 2, and multiply it with root 3 over 2 1/2, negative 1/2 root 3 over 2. So let's go ahead and do that. This row times this column. Root 3 over 2 times root 3 over 2, that's going to be 3 over 4, negative 1/2, that's 1/4. Add them together, we get 1. This times this, that's going to be root 3 over 4, negative root 3 over 4. Add those up, we get 0. This times this, we get root 3 over 4 and negative root 3 over 4. Add those up, we get 0. And then this times this, that's going to give us 1/4 plus 3/4. That is going to be 1. Check. So this would tell us that A equals root 3 over 2, 1/2, negative 1/2, root 3 over 2 is orthogonal. So this is a special sort of designation of a matrix. You guys have encountered a lot of special matrices. We know that there's things that we consider upper triangular, lower triangular, diagonal, symmetric, skew symmetric. If you've looked at the suggested exercises, there's mentions of things called idempotent matrices, nilpotent matrices. Now you've seen one called an orthogonal matrix. And orthogonal matrices are important because they have this very strong connection between the inverse and the transpose. All right. The last thing we'd like to do in this section about sort of inverses is establish that we don't need to do this double check every time. We sort of mentioned right at the beginning that it turns out that for inverses, if you multiply on one side and it works, it will work the other way as well. But we've never proven that. So it's now finally time to establish that if A times B equals the identity, then that B is guaranteed to be the inverse. So let's go ahead and do that. So this theorem says let's let A and B be n by n matrices such that A times B is equal to the identity. Then A is invertible and A inverse equals B. Once we've established this theorem, you can stop checking the inverses on both sides. You just have to check on one side, and this theorem then guarantees that if you show that it works on one side, then you're all good. So this proof is a little bit weird though, but it does introduce a very, very important concept. So to do this, we're going to assume AB equals the identity. And our goal is, we need to show that A is invertible. And of course, we also need to show that A inverse equals B. Okay, so what we're going to do is we're going to let B be any column vector. So we're going to let little b be any column vector. Then we're going to consider that if we do AB times that little b, that's equivalent to in times that little b, which has to be equal to b. So what that tells us is that if we sort of look at that, we have AB little b equals b. Not a huge sort of result, but I'm going to rewrite that a little bit, and I'm going to view that as A times BB equals B. Now, what I want to notice here is that this means, right, if we have that statement there, this means the system of equations AX equals B always has solutions for any little b. So this will always have solutions. How do I know that? Because if I plug in big B times little b in for x, I would get A times big B times little b, and we know that that's equal to b. So that means that this system equation always has solutions. And we can say, namely, x equals capital B little b. Okay. Now, this doesn't mean that for some b that this thing has solutions. This means that for any b, this has solutions. Well, this turns out, this means that rank of A is equal to n. Now, you might say, how can we make that jump there? How can we say that since this system of equation always has solutions? Notice I didn't say unique solutions. I said it always just has solutions. How do we know then that rank of A is equal to n? Well, it's actually by doing a little bit of reverse logic. If rank of A was less than n, right, that would mean that there were some 0 rows in that matrix A, which would mean if we picked a B that corresponded to having a non-zero value in the same row as one of the 0 rows of A, well, then we'd have a 0 row of A was supposed to equal a non-zero value. That's impossible. But we know it always has solutions, so we know that that never happens. That means that there can't be any 0 rows in A, otherwise not every B would give us solutions. So since there can't be any 0 rows there, and A is n by n, that means its rank has to be n. So this is actually a really important equivalence. So this is just an equivalence I want to make note of here. If AX equals B has solutions for all B, and A is n by n, then rank of A is equal to n. So this is a very sort of important connection here. If AX equals B has solutions for every B you could possibly think of, and A is n by n, then the rank of A is equal to n. And again, that's because if for some reason the rank of A was less than n, well, then you could just choose a B where the B would have a non-zero value matching up with the 0 row, which is impossible. So now we know that the rank of A is equal to n. Well, that pretty much does it, because by the big theorem, right, we know that this implies that rank of A equals n implies A is invertible. So we know A is invertible. So that basically does it for us, because once we've done that, we know that A is invertible. So there we go. So this tells us, so if AB equals in, then A is invertible, and B equals that A inverse. How do I know that B equals A inverse? Well, remember, inverses are unique, so since this thing would satisfy being the inverse, it has to be this. So this tells us now that we've established this theorem, that if you check the multiplication on one side, so you multiply on the right-hand side or you multiply on the left-hand side, doesn't matter which one, if you do that and you show that it equals the identity matrix, you can now say, oh, that means it's invertible. You no longer have to check multiplying on both sides. Okay, last sort of little result that I'd like to do is based off of this, we do get one nice sort of corollary. If you look back at one of the properties earlier, we said that if you have individually invertible matrices, then the product is invertible. It turns out that the opposite of that statement is true too, meaning that if the product is invertible, then the individual components have to be invertible. So we can prove that now that we have this theorem. So as a corollary, we're going to say let A and B by n matrices such that the product is invertible, then both A and B are invertible. So we're going to prove that if your product is invertible, the components need to be invertible. We already proved as property 2 that if the components are invertible, then the product is invertible. But this reverses that statement. So to do this, what we're going to do is we're going to actually just claim, or we should write out our need to show. So we need to show, or I guess we get to assume A, B invertible. So A, B inverse exists. We need to show A, B invertible. So we need to show A inverse, B inverse exist. So to do that, we're just going to make claims for what these should be. We're going to claim that A inverse is actually going to be B times AB inverse. And we're going to claim that B inverse is AB inverse times A. So we're just going to directly claim that these things will work. Now we can actually show that. So note, if we do A inverse, then that's going to be AB inverse. And by the definition of AB inverse multiplied with AB, we know that that's going to be the identity matrix. Now, do we need to go show that A inverse A equals the identity matrix? Well, we don't care, because the previous theorem says that as soon as you've shown the multiplication one direction, you're all good. So, by previous theorem, A is invertible. Once you've shown the multiplication one way, again, we did A times A inverse rather than A inverse times A, we're all good now. Let's do the same thing for B. So let's just note that B inverse B is AB inverse AB by our claim. And notice that that's AB inverse with AB. So by definition of the inverse, that's the identity. So again, so by previous theorem, B is invertible. Again, there's no reason now, since we established that previous theorem, that we have to consider B times B inverse. As soon as the multiplication works one way, we know it's automatically invertible. So in this video, we've sort of established a lot of properties of the inverse. A couple major ones, of course, are the fact that the inverse of the inverse is the original matrix, that the inverse of a product is the product of the inverses, just with the order of multiplication reversed, and that holds for any arbitrary number of matrices. We also proved that the inverse commutes with the transpose, so you can do the inverse of the transpose or the transpose of the inverse. And probably most importantly from a computational standpoint or from a verification standpoint is this theorem right here, saying that as long as you can show the multiplication on one side results in the identity, then you're all good for knowing that something is the inverse. So this wraps up section 2.6 from your textbook, which is basically the sort of full discussion about the inverse of a matrix. In our next video, we'll be moving into section 2.8. We'll be skipping 2.7 for our course, so we'll be moving into 2.8, which sort of summarizes all the results we've established so far about systems of equations, invertibility of a matrix, and the rank of a matrix.